So, Carlo, I'd like to ask you about what you said about consistency. You got the system, an observer looking at the system, and then a bigger observer looking at the observer. Let me ask you, let me maybe give an example. When you were invited to come here to give a lecture, let's say you weren't sure whether to accept or not, and you decided, look, why don't I just measure the spin of a particle in the lab? If it comes out up, I'll accept. If it comes out down, I won't accept, okay? Now, presumably in some standard quantum mechanics description, there's a wave function where, in a sense, in one branch, you accept, you're here, you give the talk, and the electron has spin up, and there's the other branch where it's the opposite, okay? However you want to interpret that wave function. Now, it sounds as if you're saying that, well, relative to the electron with spin up, it's a fact that you're here and gave the talk. Something like that. But let me ask the further question, which I really want to get to. Let us say now that some super observer, it might be some advanced being that exists now or in the future with some super technology, performs what we would call an interference experiment between these two branches. Now, presumably you would say that relative to this super observer, there is no fact of the matter as to whether you gave a talk here or not. Because for him, the two realities, or however you want to put it, are interfering. There isn't one or the other, there's an and. Now, so it seems like the logical conclusion of this, that you would say that it could be that for other intelligent beings, now or in the future, it is not a fact that you are here today giving this lecture. And would you agree with that? And if you do, does it not make you feel uncomfortable?
The answer to the first question is yes. The answer to the second question is no.
Well, Carlo, what can I say? You've managed to jump through many hoops, which I doubted could be jumped through. So, but here's, I think, what is a central objection to me in the way that you're phrasing this. I would say that physics is often bound up with schematic descriptions, and surely is not concerned with tautology, with absolutely everything that there is, but is concerned with relevant, okay, let's look at large degrees of freedom of the universe, and is concerned with questions of measurement and observation, and forgets about all of the rest of the stuff in the universe, goes to a highly schematized description, which just concerns a measuring apparatus and the large-scale degrees of freedom of the universe, and attempts to model those as a dynamical system and extract meaningful information. It seems to me that this is very much historically how fundamental physics has worked. Now, in that framework, it seems to me the fact that one has omitted certain, almost all of the universe is only focusing on those skeletal fragments of the universe, is entirely appropriate, and yet carries with it, because we are dealing with the entire universe, the suggestion that to bring in more stuff would be irrelevant. It would be irrelevant vis-a-vis an understanding of how these large-scale degrees of freedom interact with the measuring apparatus. It's just not going to impact upon that evolution. Now, if you do that within conventional quantum mechanics, it seems to me it is illegitimate to invoke an external observer. You do need some definite rules as to how that interaction is to proceed, and I don't see that your framework provides them.
I think, translated in the language that you like, what I'm saying is that, look, there's a universe, I am in a branch, forget the other branches. In this branch, there is the universe plus my apparata. I have some physics that describe the interactions between my telescope and the scale factor, because I count the number of galaxies, I see the light coming. So I have some concrete physics that tell me how my telescope and me, I mean, not me mentally, me physically, interact with a large-scale degrees of freedom. So I have a description of that. That's a physics.
But what are the definite rules? I have the unitary evolution of the state.
The definite
rules.
The definite rules.
What is your definite rules?
The definite rules are the one I read in is Bohr. Is where one I read. So what I'm saying is take.
Invoke an observer, an external observer.
That's right. What I'm saying is take Bohr, quantum mechanics, the one you study, and instead of thinking that there is a special object which is observer, because it's Wigner mind, because it's macroscopic, because it's classical, just democratize Bohr. With respect to any system, you could play I say that quantum mechanics is about relation within this system, one which Bohr would call the quantum system and one which Bohr would call the classical system, which is a thing being affected about. But what is going on is fact of the matter that happens in this interaction. So I'm not doing anything strange. I'm saying if you want to describe the universe, you have in the quantum universe, you have a Hilbert space for these large degrees of freedom, a set of observables for these large degrees of freedom, which describe what? Describe the physical interaction between these large degrees of freedom and my telescope. For instance, I have a telescope that measures the temperature of the cosmic background radiation. So it spits a number. So the fact of the matter is a number, which I interpret as a property of the system. And I want to say, this is the number. So I want to just talk in terms of actuality, not in terms, it's a choice, but I think it's a more useful choice. It's like in David Lewis. I can say that all possible worlds exist and one is actual. It's fine. I mean, I cannot convince David Lewis that this is not a good way to go. In fact, it's thanks to you that I got into David Lewis. Or I can say the actual world is what I want to call real, what I will call existence, and the other I'm happy with modality, and what I don't understand about modality is just happy with that. So I'm happy, like most of the philosophers, to not follow Lewis and just leave the rest of the branches, the rest of the possible worlds in a lesser ontologically heavy status. The same thing I would like to do with the other branches. What happens, happens.
Thank you. I really, really enjoyed your talk. I have two questions. One conceptual first, and then a technical one. Conceptually, my sense, comparing your view and my view, I know we've been invited here to disagree with each other, but my sense is that we actually don't disagree on anything of substance, merely of emphasis. So if we look, for example, at that other version of Carlo Rovelli who decided not to come to the meeting, or maybe another observer who lives on a galaxy outside our Hubble volume, or even some guy who lives on Andromeda, I completely agree with you that it's not useful for him to factor us into his density matrix, because we won't have any effect on him for 3 million years when he'll be dead. But first of all, I think it would be a little bit rude for him to just say that we don't exist just because he doesn't find us useful for him. And second, I didn't go into physics just because I wanted to do only useful things. Sure, it's useful, but the main reason I'm doing physics is because I love it, and I find it just super interesting to try to understand a little bit better what's really out there and, you know, my place in it. So my first question is just to what extent you would agree with the fact that it's just that you're simply not interested in so much in that question of what's really out there if it's useless, which I respect, you know. And the second question I have is the technical one, because you said that you don't believe that just a wave function and a Hamiltonian operator is enough structure to derive everything that we observe. So I'm curious to hear what additional structure you think is necessary, whether you think we also need a lot of what I call many words, a lot of Niels Bohr kind of stuff, whether you need some sort of semi-classical world and apparatus or whatever as an extra structure, or whether you think the only extra structure we need is a more mathematical structure. Do we need 2 more operators or infinitely many more? Or what do you think we need in addition? Okay,
thanks for the nice comment. The two questions. The first is the answer to the first is this. Yeah, I think that the difference is only a difference in emphasis. I agree. I would add, however, and this is that the emphasis is not just on me being less interested in the other branches, but is also in the fact that I would insist that more structure is needed than just the... And this takes me to the second question. So what the extra structure? I think that the extra structure is an algebra of observables in the Hilbert space. This is a mathematical. And the physics is that this algebra observable has an interpretation. So the Hilbert space is always the Hilbert space of a system from this point of view. And the algebra observables represent the possible interaction the whole system can do with S. And the spectrum of this is a possible outcome of the interactions. And so it's not of little importance. This extra structure is of crucial importance. So for instance, if I have a particle, once I have the Hamiltonian, the position operator, and the momentum operator, then I have everything. I can distinguish an Hamiltonian with a bump in the potential from an Hamiltonian without a bump in the potential from the commutation relations of the one with the others. If I remember correctly, an Hamiltonian with a bump of the potential in down has a different spectrum, but up has not. I mean, somebody is fresh in quantum mechanics could be. So some aspect of the potential are written in the spectrum, some other aspect are written in the commutator with Q and P. And Q and P are what? Are the possible things that can interact with a particle. So I think that a system like a particle is characterized not just by its Hamiltonian, but also by how I can interact with it, which is Q and P, or something else. So this is a...
I think that my question has already been asked by Max. It was his first question, but just to put it again for clarity, I think it's also my neighbour's question, so it may be many people's question. I had the sense that there couldn't be an empirical difference between your view and an Everettian as regards an experiment, at least when you consider not heuristic guesses for the future of physics in further development, but quantum theory as we have it now. And since the relational view was part of quantum tautology, and in fact, happily, the top sentence that we now see states that quantum tautology, a valuable enterprise, is nevertheless not a piece of physics. Would you agree there isn't an observational difference between relational view and Everett?
Yes, completely. I think that, I mean, of course, we don't know if quantum mechanics is right? Quantum mechanics could be wrong and it could be superseded by another theory. I think that if it is superseded by another theory, we're not going back to classical theory. It will be something even more strange. But this is just what I think. So I agree that there is no measurement that distinguishes these two ways of viewing things. Completely. Which does not mean it's not interesting, because we are confused about quantum mechanics. So the game here is, can we find a way of thinking about quantum mechanics which is less confusing to us? I think that Bohr is horrendously confusing, because it tells us there's a classical world, but it also tells us a classical world with quantum mechanics. So I think that both many word and the relational view are ways to try to deal with that. I mean, how can the observer be quantum, also quantum? We know that in some sense it's quantum. So how to deal with that?
I just wanted to make some comment about this all there is Hilbert Space discussion we've been having. I mean, here's what strikes me as slightly strange about that way of thinking about it. I mean, there's a sense in which there's no interpretational problem in classical mechanics. The phase space point represents physical reality. Its evolution represents what physical reality is doing. But equally, I mean, it doesn't follow from that somebody committed to classical mechanics in a standard realist way need be committed to the idea that all there is a 2n dimensional space with very little structure on it and a single function on that space and a point that moves in that space. I mean, phase space is a state space. The whole point of the theory is that we represent the entire system under consideration by a single point, and we code all of the other stuff, all of the features of that system in properties of that space, and the way we code it is going to vary from theory to theory. And so it seems similarly in in quantum mechanics, the content of something like the Everett interpretation is to say Hilbert space is a state space, it's representational in just the same straightforward, observer independent, dispositionally independent, whatever way that the classical mechanics is. It's still a state space. All the physical features of the system are represented by that point. That point's evolution is supposed to be doing something physical. Now, it's a further question, and probably a quantum theory dependent question, quite what physical reality is being represented, but that per se doesn't seem to be part of the Everett interpretation, and that per se might well have a different answer in quantum field theory, from non-relativistic quantum mechanics, from quantum cosmology, and so on. And similarly, the project of supposing that we can actually recover everything from the Hilbert space and the spectrum of the Hamiltonian, I think that's an interesting project. It might be right. I'd like to see it being right, but it seems to me that it stands and falls pretty much independently of the Everett interpretation.
This is a good question. I think that there is exactly the same discussion in classical mechanics, and I think the same confusion is made in classical mechanics. If you read a book of classical mechanics, you can find in books of mathematicians, more mathematically minded people, a classical system is given by a phase space, defined in way there's a symplectic space up to its symmetry, etc., plus a flow, an Hamiltonian flow, and Hamiltonian fit. I don't think this is a good characterization. I think that a classical system is characterized by a phase space and a preferred set of coordinates on this phase which are physically interpreted. Unless you have those, you can have canonical transformations that kill your physics. And in fact, it's well known in classical mechanics, and it's been discussed, there are papers that discuss that you can take this phase space Hamiltonian point of view in quantum mechanics and say, I don't remember the case, but a harmonic oscillator is the same as a free particle. No, it's not the same as a free particle, because Q and X are variables, Q and P are variables which have an interpretation, and the Poisson bracket between Q and H are different in the two cases. So I am with you with what you said, but I would drive it in a slightly different direction. Namely, also in classical mechanics, I think one has to be careful in what is, if you want to read everything from the mathematics, you have to specify more about the mathematics. You have to specify the Hamiltonian, the phase space, or the Hilbert space in quantum mechanics, and a preferred algebra of observable. These are the ones which represent what? Which represent the way you can, if you have, from an instrumentalist operational point of view, but I don't want to be neither instrumentalist nor operational, of course, what you can interact with the system. So these are the how it's interpreted. And I would say this is the reality of the system. The reality of an electron is to be somewhere at some point, sometimes, and to have perhaps a momentum at some point and sometimes, which is how it affects, how it hits the screen, and not just an abstract point in phase space without preferred coordinates. So yes, but somehow driving in the opposite direction.
I think we're running quite a bit over time.
Thank you.